Hi guys, and welcome back. So we are getting very close to the end of your Astronomy Unit 1. This is Lesson 7, and you've just got one more new lesson after this, and then we will be reviewing for your Unit 1 test. So as always, you should have downloaded your interactive notebook pages for the day, and you will be filling in your guided notes for the sun's energy. So just to review really quick, yesterday we learned the difference between fusion and fission. So remember, fusion is when those lightweight atoms come together and then it results in radiation energy from the sun. So fusion happens naturally in the sun. It's where the sun's energy comes from. Okay, so we're going to be talking a little bit more about that energy today. So we need to talk about something called electromagnetic radiation, and this is a type of energy in the form of rays and waves. So light, when we think about light, if you think about a night light or a lamp or light from the sun, light actually exists in a wave. So there is a short video here that you guys can watch on your own time, but it kind of just goes through the electromagnetic spectrum and the different kind of rays and waves that there are. Okay, so the electromagnetic spectrum, when we talk about this is the arrangement of the different types of electromagnetic radiation, like a pattern. And these are arranged according to a wavelength and frequency, but we are going to focus today on visible light. So this is what our electromagnetic spectrum looks like. So here we've got waves with lower frequency. Okay, so these are radio waves. These are invisible. Okay, this is invisible. We can't see it, but radio waves would be like what transmits music on the radio. Then you have microwaves. Okay, these microwaves, if you think about your food being microwaved. Then we have infrared radiation. Again, all of these are invisible. We can't see the waves that heat up our food. We can't see the radio waves. We can't see infrared without a special camera. And then here, in this one specific section of these wavelengths, we have visible light. So that's where we see light and we see different colors as well. As we move on, we're getting into a higher frequency. These are ultraviolet rays that come from the sun, and you guys have probably heard about UV rays before. They can actually cause cancer. They can penetrate your cells in your skin, and they can act as a carcinogen. That's why it's important in the summertime to wear sunscreen. And then as we get into an even higher frequency, you've got X-rays. So this is what we use to take pictures of the inside of our bodies to see our bones. And then we have gamma rays. So I don't know if anybody's a fan of the Incredible Hulk, but gamma rays are what the Hulk like absorbed or whatever to get his superpowers. That's not true. If you were to get hit with a bunch of gamma rays, chances are you would get cancer or you would die. So you don't want to be exposed to them. X-rays can also cause cancer. But, you know, if you think about when you go to the doctor, if you've ever had to get an x-ray done and you have your x-rays taken, the technician always is wearing a protective vest, and typically they'll either stand outside the door or they'll stand behind a protective room. Now, if you're getting one x-ray or a few x-rays, it's not going to hurt you. But technicians that take x-rays day in and day out, being exposed to those rays, it can cause cancer. So if we look, we've got lower frequency waves on the left-hand side, so the radio waves. Lower frequency waves down here have less energy. So on the left-hand side of the spectrum, these are lower frequency and these are lower energy. And then as we move to the right-hand side with our X-rays and our gamma rays, we have higher frequency and more energy. Okay, so this is just another kind of depiction for you as we go from our radio waves to infrared to visible light. So this is all that we can see with the human eye. And then UV, X-ray, and gamma. And if we take a look at these patterns, again, on the left-hand side with the radio waves, this is less energy. So these waves have less energy. And then all the way up to gamma rays, which have more energy. When we talk about frequency, we're talking about how many waves kind of pass through a certain point in a fixed amount of time. So let's say that you're looking at the amount of radio waves that pass through you in 5 seconds versus the amount of gamma rays that could pass through you in 5 seconds. You're going to get a lot more gamma rays and a lot more gamma radiation to pass through you in the same amount of time because these gamma rays have a higher frequency. Okay. So again, we've got our visible light spectrum in here, and this is kind of blown up to let you see it. So visible light ranges from the red all the way down to the purple. Do you guys remember the like the colors of the rainbow, the Roy G. Biv from elementary school? So if we look at our visible light spectrum, red has the lower frequency, okay, so longer wavelengths and lower frequency for red light. And then blue has shorter wavelengths and higher frequency. Okay, so as we move from left to right, our wavelengths get shorter, and the wavelengths are just the amount of space between from crest to crest, so from peak to peak of each wave. Okay, so longer wavelengths on the left, shorter wavelengths on the right. Well, what does this have to do with astronomy? Remember when we talked about the Big Bang and we talked about the red shift, the evidence that the universe is expanding from the Doppler effect or the red shift is that as galaxies are moving away from us, their light is being bent into longer wavelengths and therefore appear to be red. Okay. Frequency, again, is just how many times a particular wavelength will pass through a particular point. So remember, if it's longer wavelengths and lower frequency, there will be less waves passing through you, okay? So anytime you have smaller numbers for frequency, this is going to be your indication that these are going to be higher energy, okay? And then this is just an image of what happens if you guys have ever had a crystal prism. You can actually take white light, because white light has all the colors of the visible spectrum, and then you diffract the wave patterns to see the visible spectrum, which again ranges from the red to the purple. The red has lower frequency and longer wavelengths, and again here at the blue-purple end, higher frequency, shorter wavelengths. Spectroscopy is just the study of light that depends on wavelength. And there are different types of spectrums depending on the conditions of the gas, so temperature and pressure. I don't need you to know that much about spectroscopy, just that it is a study of light. The Doppler effect is similar to the red shift, but it's just the change in wavelength of a wave that is emitted from a source that is moving away or towards an object, okay? So this works for sound because sound is also a wave, just like light is. So if we look, let's say that you're sitting on the street and an ambulance is coming towards you. As the ambulance is coming towards you, the waves that are being emitted are small wavelength and high frequency. Okay, so it's more of like a high-pitched sound. But then as it moves away from you, the waves are bent to be longer and have a lower frequency, so it is a different sound. It's distorted. This Doppler effect is why we see the red shift in the galaxies that are moving away from us, because as they move, the wavelength of the light is distorted towards the lower frequency end, so the longer wavelengths. So that's why it appears red. In astronomy, the Doppler effect is used to determine whether a star is moving away from Earth or towards Earth. And the movement is determined by the length and the color of the wavelength. So again, if something is moving away from Earth, it'll look red. So the light will be shifted towards longer wavelengths, lower frequency. And if an object is approaching Earth, it'll appear blue. So it'll be shifted towards shorter wavelengths and shorter frequency. Okay, so appears blue because if something's moving towards us, it appears blue because the wavelength is shorter. This is called the blue shift. And then if it's moving away, it appears more red because the wavelength is longer, called the red shift. And remember, the red shift is the evidence that supports the Big Bang Theory and that our universe is still expanding. Okay. So Earth has something called a magnetic field that will protect planets from harmful effects of radiation. And we'll talk about this a little bit more next week, but the sun emits a lot of radiation, and there's something called solar wind. If all the solar radiation from the sun were to hit the Earth directly, we would not be able to survive. We would not have any kind of way of surviving as we know it. What protects us from the sun is a magnetic field. So there is a magnetic field that's emitted that spins around. It kind of comes up from the poles and spins around the Earth, and it acts as a shield, and it deflects a lot of this radiation. Some of the radiation still comes in and it heats the Earth, but a lot of it's deflected. Okay, and we'll talk a little bit more about Earth's magnetic field next week. And then an aurora, the polar lights, northern lights, or southern lights, this is a phenomenon of the diffraction of light that you can see towards the poles. It's actually really pretty. I've never seen it in person, but it is on my bucket list. So what happens once solar radiation does reach the Earth? So let's say we've got 100% of the radiation coming in. About half of it is absorbed at the surface, and this is what heats our atmosphere and causes our temperature. So remember, if we're in summer, we're getting more radiation coming in because we're tilted towards the sun. So we would be getting more of this absorption and more heat. Okay. About 6% is reflected by the atmosphere. 20% is reflected by clouds. That's why it tends to be cooler on cloudy days. And then 4% is reflected from the surface back into the atmosphere. And then about 19% is absorbed by the atmosphere and the clouds. So heating land versus heating water. Heating water takes a lot longer. So there's more evaporation. You've got the mixing of warm and cold. And then it takes about 5 times longer to heat that versus the land can kind of absorb that radiation pretty easily, and it can heat up very quickly, especially if you're in a man-made area with a lot of asphalt. So anything with a lot of asphalt will absorb a lot of radiation and heat very quickly. The last thing we need to really talk about in terms of what light is important for, light is one of the components in photosynthesis, okay? So we know that plants make oxygen, right? So plants produce oxygen that organisms on Earth use to breathe. Well, light is a necessary component for this process. So if we look, this is the chemical reaction, okay, for photosynthesis. And what happens is that plants absorb light energy from the sun. They also take in CO2 or carbon dioxide from the atmosphere, as well as water, okay? And then they convert it to a usable form of energy. We as humans can't take energy from the sun and use it, okay? We have to get our energy from elsewhere. We get our energy from plants and the things that eat plants. So first, the plants have to convert it into usable energy, and that usable energy is glucose, which is sugar, okay? And they also produce the oxygen that we breathe. So what I need you to know in the grand scheme of this, because you will learn about this in depth when you get to biology next year, I need you to know that sunlight is an important part of photosynthesis that helps the plant make food and oxygen, okay? That is the main takeaway. And that's all I have for your Unit 1, Lesson 7. If you have any questions, let me know. I highly recommend watching the electromagnetic spectrum video at the beginning of your slides. But with that being said, we are almost to the end of Unit 1. Let me know if you have any questions.